big break coming up and everyone's kind of just throwing their hands in the air.
I do know a few people doing that.
Me too. All right, so we are gonna be wrapping up chapter 17 here today. There's really not too much to do in terms of, let's say in terms of concepts that are going to be extremely important for the next exam. If you remember, at the beginning of this chapter, the first thing we talked about were two definitions of acids and bases. And we talked about the Arrhenius definition, and we talked about the Bronsted definition, and that's kind of where we've been hanging around, right? We've been talking about protons being transferred and this kind of stuff, right? That's our Bronsted definition of things. There's another definition, which is Lewis acids and bases, and it's an extremely important topic. But for the most part, we don't really talk about it too much in this class. Towards the end of the semester, just kind of depending on the timing and that kind of stuff. The last kind of chapter, we go through some organic and some inorganic chemistry, and we'll see this kind of Lewis acid base stuff rear its head again in the inorganic chapter there, right? But in terms of the next exam and the next couple of chapters, it's really going to be focused on Bronsted acid-base stuff, right? That's what we've been doing. So, but we'll talk a little bit about that other definition here and just kind of what happens with it and how do we look at it and how it does relate to what we're talking about here. But then it'll kind of just go dormant until we get back to organic chemistry in some way there. And let's see, and also last time we got to the idea of where does the chemistry change, right? When we're doing weak acids or strong acids, and weak bases and strong bases, right? You know, how does that start to affect how we have to approach different types of problems, right? And we'll finish that up today then, and we'll have a couple of practice problems and stuff just to kind of hopefully drive the point home, right? If you guys haven't seen, right, the quiz should be open for you guys. So that should be available for everyone there. Nice, easy quiz, right? So just going through some of the stuff that's from the book there, pretty straightforward. One of them you'll have to do a quadratic for, so just make sure you guys are got that ready to go when you guys are doing your work for that one, okay? What's up?
Is it due tonight or this week?
Tonight. Yeah. So yeah, I think it's always at like 11:59 or something. So get that done, get that wrapped up, and then Friday we'll keep looking through some more problems and kind of put the finishing polish on this chapter here. And then when you guys get back, we'll start off with one of the more trickier chapters. Not necessarily in terms of concept, but just more with keeping track of what in the world we're trying to do to begin with, right? But we'll talk about that. We'll talk about that when we get there.
Is that going to be on the next exam?
Yeah. Yep. So all the equilibrium stuff. What's up?
Just for set reference.
Yeah.
The next exam is going to cover approximately chapter like.
So we the equilibrium stuff that we did, right? The equilibrium chapter, and then the acid base, and then I think the next chapter. What do I call it? Like aqueous ionic equilibrium or something like that. Whatever chapter 18 is. Yeah. Okay, so there's that. I think that's kind of all I needed to chat with you guys about before we got started. I think so. Okay, so let's get started with prayer, and then we'll see where we can get to today. Lord, we just thank you yet again for another day, another gift, another opportunity, another chance. Lord, we just pray for the things that are just distracting us today, Lord. We know that you want us to be good workers, you want us to be good servants, and you put these tasks before us, Lord, so that we can accomplish them and with a smile on our face and just understanding that the work that we do is for you, Lord. The gifts that you give us, the talents that you give us, the time that you give us, Lord, is all for us to work for you, and we just pray that we keep that in our hearts, Lord. Just help us to focus why we're here, and help us to focus on what we're doing, and how we can serve you and whatever we may be doing, Lord. So we just pray these things. We pray just for a peace of mind, just a calm heart and calm spirit. And we pray that you just renew us today, Lord, and just give us the energy that we need just to finish this up. And we just pray this in your name. Amen. All right. So we had gotten to this idea, which is going to be core to the next chapter here. What happens when you start to put weak acids and bases together, right? The next chapter, we're going to get into the idea of buffers, and we're going to get into the idea of titrations, which buffers are essential, right? Anytime you guys are going to be talking about biochemistry, biology, all these kind of things, it's, buffers are really, 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 really important, right? And they're all based off of this idea of equilibrium, right? What's the pH and how do they react? Why do they behave the way they do? All this kind of stuff, right? We'll talk about buffers there. And we'll do more K stuff. Shocking, I know, right? But this is kind of what's at play behind the scenes there, okay? And so we had talked about, I believe, strong acids and weak bases, and here we go to strong bases and weak acids. And we said that when we mix an acid and a base together, a neutralization is going to happen, right? The acid is going to react with the base, and if we make the assumption that we have an equal molar amount of our acid and base, right, then all the acid, all the base is going to react, but then we're going to be left over with some of our conjugate base over here, right? And depending on the strength of that conjugate base, or, if we're looking at the other direction, the conjugate acid, that's going to affect what the pH is at the end of our neutralization reaction, okay? Strong acids and strong bases together, they neutralize completely, and we just end up with a neutral pH of 7, okay? But the neutralization reaction of a strong base and a weak acid may not have a pH of 7 at the end. That's the difference, right? So don't get confused just because you see the word neutral, you think pH of 7. I mean, that's true, but we're not talking about necessarily the pH getting to 7. We're talking about reacting all the acid and base together. That's what it is, okay? And so we made the point, the very important point, that weak acids tend to make stronger bases. And if you're a stronger base, then you can go on to react with water. You might end up generating some hydroxide, right, which is going to affect the pH, right? So because pH plus POH, right, equals 14, right? So if we make hydroxide, we're going to be raising the pH above 7, right? All right. And I believe we kind of ended here last time, just to kind of drive that point home, right? We talked about calculating the pH of a sodium carbonate solution, and I gave you guys the KB over there, and then we just talked about kind of how we set the stuff up and go through and do the calculations with it, right? So nothing really too shocking with this stuff there, right? The only point is what? That this will affect the pH, right? Having this carbonate around in solution is going to affect the pH. It is basic, so it's going to raise the pH above 7 is what it comes down to, right? So how do we go through and do this stuff? Well, there's something called an ice table, which I know is, again, shocking, right? And so we just went through this real quick, set that up. There's your minus x's, all these kind of things, yada, 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 right? So hopefully you guys are starting to get a little bit more comfortable with setting up ice tables, especially in this chapter. The ice tables aren't that complex, right? Because all we're doing, for the most part, as long as we're paying attention, right, is that we're reacting a monoprotic acid, right, with a single equivalent of hydroxide, right? So we're reacting one equivalent of acid with one equivalent of base. Okay? So all you have to pay attention to is how many protons you guys are transferring in between the two. Right? If something changes, then we have to go through and either set up 2 ice tables for each proton, or we just have to change the stoichiometry. Okay? We'll talk about that a little bit more in the next next chapter also. All right? So just paying attention to stoichiometry and thinking about it when you're writing it down. Right? You guys get what I mean with that? It's what I mean is there's a habit that we develop, like, oh, these are all solved the same way, blah blah blah, and just write them down, and you're just kind of not processing what you're doing with it, right? So just take a minute every time you write down an ice table and think about these things that go into it. Okay? That's all I'm asking you guys to do with that. All right, so we got that. We got that right there. We got it all finished up. Cool. So on the other direction then, weak bases and strong acids, the exact same thing's going to happen, right? What we end up doing is reacting our weak base with the strongest acid we can make in water, right? H3O+, right? And what we end up doing is we make a a stronger-ish, right, a strong enough acid that it can dissociate to make some quantity of H3O plus in solution, right? And if you make some quantity of H3O plus, likely you're going to make the solution acidic, or the pH is going to go below 7, right? So that's the point here, right? Weak base, strong acid. We make weak bases make stronger acids, right? And so that stronger acid after the neutralization is going to dissociate to some extent, right? And then we have to go through, and I don't know if I showed it on the slides or not. Yeah. Oh, I did. Okay, so yeah, same thing coming up here, right? So if we have the pH of a 1.32 molar ammonium bromide solution there, right? We could go through the same rigmarole that we did for the other example there, right? We set up our generic equation for what's going on with the dissociation here, right? The ammonium plus water makes NH3 plus H3O plus, right? Our HA plus water makes A minus plus the H3O plus, right? That's the same generic setup that we've been doing there, right? Remember, Br minus isn't going to participate in anything here. It's the conjugate base of a strong acid, so it's just going to kind of float around and make sure things are kind of balanced is all it is, right? So we don't have to worry about that changing the pH. If there's some of these jerk questions where we have a weak acid and it's paired with an anion that's also a weak base, and then we have to set up 2 ice tables and do all this kind of stuff, it gets miserable, okay? So why am I putting this stuff in here? Why am I drawing your attention to it? Remember, this is what I was just saying, they're always thinking about what you guys have in the solution, okay? Very quick just to go to set up the ice tables and okay, this is 0.132 minus X, yada, yada, yada. But thinking about what you have present in there. What does it mean to dissociate, right? The NH4 plus is the thing that's doing something, but don't ignore whatever else it's bound to, okay? Bromide, the Br minus, isn't going to do anything in this case, right? It's a weak enough base that it's not going to dissociate or react with the water in any way, okay? But just paying attention to that is extremely important. Okay, right? So shocker again, right? Ka, products, reactants, X. We take a look at our Ka value up there, it's times 10 to the negative 10th, right? So pretty darn small K value, so we can ignore our X here to simplify our math, and then we don't have to do the quadratic equation. We get a value for X, which represents our hydronium, right, H3O plus, and so we just take the negative log to get our acidic pH that comes out of this, right? You guys starting to see patterns with things here? Are you guys starting to see patterns in how we solve these ice tables? How you could start to maybe take some shortcuts if you're very cautious. Mm-hmm. Something interesting to think about, right?
Okay, just to confirm that I'm retaining what we learned the other day. We know that there's a big difference, and we can use a shortcut because Ka is such an incredibly minuscule number.
Compared to our initial concentration, yes.
Okay.
Yep.
Thank you.
Yeah, so if you have a difference of about 1,000-ish or so, then we can easily ignore that, right? So we have a concentration of 0.1 versus something times 10 to the negative 10th, right? There's a difference of 10 to the 9 in between there. Easy, we can ignore that, right? All right. So, now the time that you guys have been waiting for, where you just throw up your hands and say, eeny, meeny, miny, moe, right? So what I mean here is, what if we have a weak base and a weak acid? Well, I'll go ahead and break the good news for you guys on this one. Like, I'm not really going to ask you guys this stuff. Why?
You don't care?
No, it's not that I don't care. It's just this is, I mean, what's the idea that's behind this here, right? Well, we're just comparing the acid to the base, right? We just need to figure out which side is weaker, but not as weak, and then stronger, but not as strong, all this kind of stuff. And so there's a lot of just kind of qualitative assessment that goes into this, right? I mean, it's important, and we need to think about it, right? But at the end of the day, there's, these types of questions don't test anything, aside from, can you guys just compare a value of Ka to the Kb and see which one is bigger or not, right? That's all it's really asking. So what's the concept that's behind this? What is important to think about, if we step away from this idea here for a minute, what is important to think about is remember that if you're trying to make a relative assessment about which side of the equilibrium is favored, right? Remember we said that if you're going to be thinking about which side of equilibrium is favored, the side of the weaker acid tends to be favored in the equilibrium, right? That is important. Now the book talks about it in the opposite direction that I do. The book says that it favors the stronger base. Well, that's true, right? That's absolutely true. We're saying the same thing just from different directions. So if you want to say it favors the stronger base, that's fine, right? If I think it favors the weaker acid, it's just kind of the way that I remember it, right? So either way is just fine. Good? So that's the important part to think about on this. Other than, like even on the slide, I'd say this is just all qualitative, right? There's no math involved with this, really, so don't really know too much else to kind of mention about this stuff to you guys. Okay, so here's kind of a slide that summarizes everything here, just to kind of keep in your back pocket. Why do I give this stuff to you guys? Well, remember, the most important thing you can always do after you're done with the ice tables and thinking about your Ks and dealing with the panic, right, is always take a moment at the end and say, does my answer make sense, right? So if you're doing a strong acid, strong base, where pH should be pretty darn close to 7 at the end, okay? That's all I'm trying to get you guys to see here with this. How do you know when your answer is correct, right? Remember, I've told you guys this before, and I'll keep telling it to you guys until you believe me, right? There's a lot of math involved in Gen Chem 2. I think you guys believe me on that one, right? But what I'm saying is, we go through, we do this math, it's complex, it takes time, and then we're happy when we get an answer. But think about what that answer means, okay? Think about what that answer means in terms of scale, how big is the number, right? And think about in terms of what units we're dealing with, right? That's going to be extremely important for you guys, okay? So we know we're dealing with pH, so our answer should do what? Lie somewhere between 0 and 14, right? So if you're calculating pH and you get 23, guess what you did? A mistake. Got it? Right, so always thinking about what our answer means, okay? Cool. So strong acid, weak base, right? We're going to have a pH less than 7, right? Weak acid, strong base, pH greater than 7, and then the pH for the weak acid, weak base is just kind of a toss-up, but we need to know all the Ks and kind of figure that out, right? Okay. All right, so here's what you guys have been waiting for, all right? So, all right, so taking a step away from Bronsted acids and bases for just a minute, we talk about, as the slide says, the most general definition of an acid and base, and this is true, okay? So in terms of the 3 definitions of acids and bases that we have, everything can be defined in terms of Lewis acids and bases, okay? Now by convention, I don't know, I have to sometimes be careful here, right? For the most part, when we talk about acids and bases, we're talking about Bronsted acids and bases, right? Where protons get transferred, that kind of thing, okay? But in general, we should be very specific and just mention what type of acids and bases we're talking about, right? Whether we're describing Lewis acids and bases or Bronsted acids and bases, okay? So let's define what a Lewis acid and base is. A Lewis acid accepts electrons, okay? So they're electron acceptors for the acids, right? So an acid is the acceptor. And then the base would have to be the donor, okay? Now something that, another definition that we kind of have to bring in because of this new concept here is this idea of a coordinate covalent bond. So what's different here is just that the electrons that are shared in the bond come from the same atom, okay? Whereas before, when we're thinking about covalent bonds, right, each atom shares 1 electron, okay? Now these coordinate covalent bonds are most commonly seen when we're dealing with our transition metals, okay? So if you go back and you think about what iron 3 chloride is, and you're like, what does a 3 mean, right? And how many chlorines are there, and this kind of thing, right? But what, right, our oxidation states and everything, very important, right? But if we think about our transition metal complexes with that, we typically think of them as coordinate covalent bonds, where the chloride is donating 2 of the electrons to the iron to make a coordinate covalent bond, okay? And in such a case, we would say that the iron is accepting the lone pairs, so it is a Lewis acid, and the chloride is donating, so it is the Lewis base, okay? So why am I telling you guys all this? Well, geez, I've got like 4 weeks of time to fill still, so I gotta just keep talking, right? But no, what I'm saying is when we're in the realm of Lewis acids and bases, we're gonna be talking quite a bit about the transition metals and the things that are bound to them, okay? Very, very, very vital chemistry comes from all of these ideas of Lewis acids and bases, all right? So if you see this term, that's all it is. We're talking about one atom donates both sets of electrons to make a bond, okay?
So you're saying by the Lewis definition, a lot of metals, or at least transition metals, are acids?
Mm-hmm. It's true.
Okay, I do not think of metals as being acidic.
Well, even a lot of metals, when you put them into water, they turn the aqueous solutions acidic by pH, right? So no, yeah, and so the reason why is kind of based off of the stuff that we're talking about here, right? So does
calcium do that? Because I know I have to dump calcium in my pool sometimes, and it causes a heck of a thing.
Yeah, I mean, I'd have to think about it. Each one has a little bit, each one is better at doing it, right? You know, there's different properties with all the metals, right? But as soon as you coordinate metal to an ion, right, you change the acidity, you change the strength of change how strong a bond there is between the oxygen and the hydrogen. And it can make it more acidic, right? So you can start to change the pH in that way there, right?
Yeah. Thank you.
Yeah. But so if we take this definition of Lewis acid and base here and kind of back it out to on the top there, the Bronsted acids and bases. I think I forgot it's a positive sign there. Just to make sure we're all good, I guess. Right? Oops. Okay. So remember, a Lewis acid is a lone pair acceptor. So if we think about this definition and back it into the Bronsted acids and bases, right? The proton, the H plus, is accepting that lone pair from the water itself, which is the Lewis base. And therefore we make our good old buddy H3O plus, or hydronium, right? So that's what we're thinking about in this sense. So that is the Lewis approach to looking at Bronsted acids and bases, okay? Down here we kind of see a more, let's say, inorganic view of how Lewis acids and bases are more practically used. And so we have a Lewis acid here with the boron trifluoride and the Lewis base there with ammonia. And when you bubble these two together, right, or if you bubble ammonia through a solution of the boron trifluoride, you end up making this kind of Lewis acid base adduct right here. And that's extremely important, right? There's a lot of stuff that we use that kind of generate these kind of adducts right there, and then go through and do some other chemistry with them.
You said that's called an adduct?
Adduct, right? Okay, so there's that. This is, boron is extremely important, industrially speaking. Cool, that's what I wanted to do. And did it twice, cool. All right, there it is. All right, so like I said, this is kind of a preview of what we'll talk about a little bit towards the end of the semester there with respect to the Lewis, the transition metals. Most metal ions tend to act as Lewis acids, although, it depends on the specific qualities of whatever the metal that we're looking at, right? And if we have something like silver and bubble some ammonia through there, we make these silver ammonium complexes. How do we know that 2 ammonias are going to bind to it? Why not 6? Right? Why not just 1? Why not 3? Right? So we'll talk a little bit about that when we get to it. Hydroxide ions are very, 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 very good Lewis bases, right? Remember, Lewis base is just a donor of electrons, right? So we're typically looking for things with negative charges, right, to donate electrons, right? And so that's what we're just trying to talk about here, right? You can easily donate electron pair to make another bond with something, right? And so that's why, I don't know if you guys do this do a titration or not, but there used to be an experiment that we did where we titrated different metal salts, right? You just sit there and you add something like hydroxide or nitrate or chloride or fluoride, right? And you can actually precipitate out the different metal ions, and you can see what the concentration is and do qualitative water testing, right? We can see how much calcium's in the river water around here, right? We can see how much fluoride's in the water and nitrates and all these kind of stuff by playing off of the Lewis acid-based chemistry that comes with the transition metals and the different things that we can add to them.
That sounds really cool.
It is, yeah, but I don't know what, excuse me, I don't know what Dr. Tong added into the semester for you guys for the lab this year.
Right now we're doing a kinetic thing.
Kinetics? Right on time, right?
Oh, no, his
he
class
said-
hasn't hit that yet.
There's no way his class
He
doesn't hit that.
said, tell Dr. H you have outdone me.
Well,
How's it that kinetics was what, the second chapter? that
They
we did?
switched to unit. They're doing rate laws and stuff right now, and they did electricity when we were doing rate laws or something like
We're really behind.
Well, we're in the cool class. That's all. Coordination is key, yes? All right. So, just for kind of reference sake and something here, right? Metal hydroxides are amphoteric, which means they can react with acids and bases. So what the world does that mean, right? So if we have these Lewis acid-based adducts here, this aluminum hydroxide, you can see in some cases where they react with more hydroxide to make a different species here, right? This aluminum anion there, or we can drop in some acid here, there, and we end up kicking off the water where we do a Bronsted acid-based reaction, where we can actually neutralize some of the acid with the hydroxides that are bound to the aluminum there, right? So, question, how do we know when that's gonna happen? Well, at the moment, you guys don't know, okay? So, we'll talk about that, like I said, a little bit more when we get into it towards the end of the semester there, when we're kind of playing wrap up and catch up and just kind of prepping you guys for what's coming next in chemistry, okay? But all that to say, there's an entire separate class that deals with all the transition metals, okay? Your progress in life, I'm gonna go ahead and plan your life for you, right? Is after you guys are done with Gen Chem, right? You guys are gonna go on to organic chemistry, and then if you guys were pursuing a degree in chemistry, we do analytical, and then you guys would go on to inorganic chemistry, and that's where you learn a lot about these transition metals, right? You guys are, we don't offer inorganic chemistry here anymore. Supposed to teach it. And it's my favorite class, you know why? Because I can teach you guys where colors come from, right?
that.
But now I have to teach you guys about boring titrations, right? So no colors there, right? Just boring clear liquids getting titrated into boring clear liquids, right? But anyway, so but all that to say is, you know, we're just scraping the surface here. All right. I think this is the last slide here. Okay. So we can also do the same kind of idea here with neutral molecules, right? So remember, or if you want to, or the important thing to remember out of this Lewis acid-based stuff is just looking for how things are reacting with respect to donating a lone pair, right? Things are accepting or donating lone pairs here, okay? So the thing at the bottom there is, I would say, fairly relevant to what is important in chemistry these days. So I'm sure you guys have heard at this point there's a gigantic argument about the impact of carbon dioxide on our atmosphere, right? And so there's a lot of research being done on how we can sequester CO2 out of the atmosphere, okay? And so and everyone always thinks that it's really difficult to do. It's not. You guys can do it at home. You get a glass of water, you get some drain cleaner, you put it in there and you just let it sit. And over time, you're going to start to see some white stuff start to precipitate out of it, right? And that's CO2 that reacted with the hydroxide that's in the drain cleaner, and you're precipitating out, right? Some, usually probably like sodium carbonate or something like that along the way, once it reaches a specific concentration, okay? It's really not that hard to do. In fact, that's mostly how it's done on the industrial scale also, right? They dissolve something called triethanolamine into water, and then they just bubble the stuff that comes out of the smokestacks through that, okay? And they capture CO2, and it's great. Why? Well, triethanolamine's pretty cheap, right? And water's pretty cheap. But then there's problems with it, right? And one of the biggest problems is, so what, that you can capture carbon dioxide? What are you gonna do with it after you capture it, right? So you turn a gas into a solid, it's a little bit easier to deal with, right? We can isolate things like sodium carbonate, right? That kind of stuff, but what are you gonna do with it once you're done with it? What's up? Rachel, you know?
Oh, I said you could feed it to algae.
Well, that's something that they're thinking about doing, right? Is can we turn the CO2 into a value-added product, right? So there's a lot of, for instance, there's, methods that we can make plastics from carbon dioxide, right? So polycarbonates is what it is. But anyway, so extremely important chemistry that's relevant to the things that we need to fix today, so to speak, right? Problems that need to get solved or problems that need to be addressed in some way, right? In fact, what is it? So recently, so if you guys are looking for a way to pay off your student loans, Elon Musk, right, put up a proposal for a team to start to, prototype how to capture CO2 from the atmosphere, right? And so I think he's giving out 10 awards of like $5 million a piece. So if you guys have nothing else to do over the next break, right, you guys can come up with some ideas and pitch it to him there, and pay off your student loans while not having to come back to school because you can go to work already, right? But it's true, right? And I'm not here to make a giant argument one way or the other about climate change. It's just I think from the Christian perspective, we were given the task of taking care of our planet, right? And so I think everybody should kind of have that view on it, no matter where you kind of sit on the impact of what we're doing here, right? So I think that's what the real argument is. I don't think you could walk up to anybody on either side of the argument and say, do you think I should throw more plastic cups on the ground? I think everyone's gonna say, no, don't do that, you're a jackass, right? So, right, but what the response of what we need to do for these things is where the questions always come in, right? How should we appropriately respond to climate change, I guess? Anyway, different argument. Fantastic argument, but there we go. All right, so that's the end of chapter 17 here, right? So let's spend a couple minutes here then thinking a little bit about some questions and kind of working through and practicing some things, right? So find the pH of a 0.1 molar acetic acid solution. All right. Typical question. Entry level question for this chapter, I would say. Find the pH of an acid. Given the Ka, right? So find pH from the Ka.
Are we just assuming that water is acting as a base?
We're always doing aqueous chemistry, right?
Yeah, but since there's no base, then are we just assuming it's reacting with water?
What else would it react with?
That's what I'm asking.
No, that's what I'm asking. What else would it react with?
Nothing?
Okay.
My brain is half on, but not entirely.
So think about it, right? What does it mean to look for a pH?
I'm fine, I'm doing an ice table, I'm fine.
No. So backing away from that, right? pH is a negative log of hydronium. Right? To make hydronium, you have to have H plus and H2O. So the H plus has to react with H2O, right? What else could it react with? That's what I was asking. Are you breaking the tape?
Oh, what is this? Little square.
Oh, nice.
Physics.
For physics, this? Really? Did you guys get that?
No.
Wait, what's the chemical?
So you're just being a dork, huh? What's that?
What's the chemical formula of acetic acid?
Ah, so good question. Do we need to know that?
No,
Not necessarily.
Not necessarily, but why is it important to ask that question?
to know if
we can
it's
balance it, we can start
Perfect, right? Right? So it's always important to look and say, hey, am I dealing with a monoprotic acid or am I dealing with a polyprotic acid? Okay? Now, I'll go ahead and tell you that acetic acid is monoprotic, right? One single proton that's dealing with it, okay? Or that's being dealt with. The other important thing to think about, while you guys are kind of jotting down your notes and thinking here, is where can we look up information about the Kas? Well, there's a giant table, well not giant, it's about half a page or so at the back of the book, right, that has a list of all the Kas. So if you're working through some practice problems, it's in there. Although, I know you guys, where do you guys go to look up Kas?
Google.
Good old Google, right? Right? But in case you guys need that stuff and you know, you're doing your spring break in, I don't know, the middle of Alaska, there's no internet, then it's in the back of your book there too, okay?
I'm going to Atlanta during spring break. Is that the
I'm
thing?
sorry, that place sucks. All right.
Yeah, but my best friend goes to Georgia Tech.
Too bad.
Finally a chance to see her all year.
Yeah, my brother went to Emory and I didn't visit him all that much. So.
My roommate transferred here from Emory.
Emory.
Oh, Emory.
Yeah. There you go. Why we can do math?
Why we can, I'm sorry, that was so
I just kidding.
Why we can drop, because I know I'm looking for Ka, it's
Yeah.
very small.
Mhm.
What if this tells us that it's reacting paper, so how can we take something out of the reactant side?
No, that doesn't tell us reacting, it says it's, oh, excuse me, yeah, sorry. I'm being dumb now, ask your question again.
Well, so why do we have to, or why are we allowed to make this that way? How come
So what does that X represent?
concentration is,
Not necessarily that's what it represents at equilibrium, but it's also part of our change, right? So it represents a change in concentration,
okay.
okay? And so if we have a really small K value, how much is our initial concentration gonna change?
Not that much.
Not that much, you're right? So we're just approximating that's gonna be about the same.
Okay.
If you go through and do the math, it'll probably come out to be like 0.099997 or something like that, right?
Okay. That makes sense.
You can always do it using the quadratic formula, right?
Yeah.
Cool. Looks good.
That's just a Florida thing, right?
No, so that's, you're taking the log of the Ka, which would give you the pKa, which is something important, but not gonna be helpful in this case. Okay? So what you need to do is find remember, the pH is basically saying, take the negative log of the equilibrium concentration of H3O plus. So you need to figure out the equilibrium concentration of H3O plus, and then take the negative log of that. So you need to set up your ice table and then solve for the equilibrium concentration.
A bagel.
Looks good, a nice ice table, waiting to get set up, alright, I like it.
About what?
I'm Steve.
Dude, I'm too brain dead to process anything, you gotta give me more information.
Okay. I just asked Dr. H, how come we can do this thing?
And Dr. Tom once had to spend over 15 minutes explaining how to do a basic cross multiplication to me. Join the club.
So remember, we have our good old friend, Mr. Generic Acid Dissociation, right? Where a monoprotic acid, HA, is dissociating in water to form H3O plus and the conjugate base A minus, right? Set this up, we don't care about water, doesn't change for all practical purposes. We assume we start out with 0 of the H3O plus, although that's not necessarily true though, is it? Remember, in water, right? In water, we do have some H3O plus that naturally exists, right, by the autoionization, okay? So behind the scenes, you guys have been dropping part of this out also, right? Technically, we do have some of this around, okay? But for all intents and purposes, we don't really care about that because as soon as we auto-dissociate to make H3O plus, that we also have OH minus one. Just something to remember though, okay? Whoops. Skip ahead of myself here. We lose some X, we gain some X, we gain some X. 1 minus X plus X plus X. Fantastic. Okay. There it is. Right, so our Ka is equal to H3O plus times A minus concentrations over our HA, fill in the blank, right? We have X, 0.1 minus X, and then what did I say, 1.8 to the negative 5. Good, right? We pause, we make an assessment. Our initial concentration is 0.1. Our Ka is times 10 to the negative 5th. Right, so there's a difference of 10 to the 4 in between there, right? So a difference of about 10,000. You everyone with me on that one? All right, so there's a big enough difference that we can do our approximation, which means we drop X out of the bottom there, right? And so then we just simplify to say X squared over 0.1 equals 1.8 times 10 to the minus 5, right? Good. And if we do a little rearrangement, I'll show you guys why here in just a second. Right, then we say 0.1 times 1.8 times 10 to the minus 5. Everybody, oops, there it is. Right, everyone with me on that? We got X equal to, I got 1.34 times 10 to the minus 3, right? A small value of X. Right, but that X represents our equilibrium concentration for H3O plus. 10 to the minus 3, right? So if we take the negative log of X here, right, we got our pH. Good? So I think I saw pretty much everybody get it, something like, what was it, 2.87, is that what it was?
Yep.
Good? So not a big concentration, right? 0.1 is not that big of acetic acid, but fairly acidic though still, isn't it? Right? Okay, now the next question is going to be completely different. Are you ready?
Or are you gonna give us KD instead?
No. So now I want you guys to, whoops. Now I want you guys to find the pH of 0.01 molar acetic acid.
Same K?
Yeah, the K doesn't change, right? K is a constant.
Wait a second. We're gonna have to do this the long way, aren't we?
See what you guys came up with.
I gotta see.
But when in doubt, right, the long way always gets you the right answer. Do it both ways, see what happens. gusto.
Hmm?
Going for the gusto with the quadratic, alright. Alright, so that's because, where you guys were studying for physics there earlier, is that what it is?
Yeah.
So you're just trying to get into physics mode here?
Oh, yeah.
Yeah, I've got an exam or quiz, or what is it? Ah. Okay. So now see what you can get with the approximation.
Hey Doc, is a quadratic equation negative b plus or minus the square root of b squared minus 4ac over 2a?
Yes, I think, yeah.
Okay. I always like doubt that I'm remembering.
No, me too, so I usually just look it up too, so.
I'm too lazy for that.
Get a tattoo. Always with you.
I'm genuinely considering getting the quadratic formula and the unit circle tattooed on my arm, just because it's causing me so much trouble.
I'll pay you not to do that.
What if I got one of those really nice temp tattoos?
I'm not gonna tell you how to live your life. So how big a difference did it make?
I hate
Right, so you get the point, right? So, which one would you rather do?
I mean, I thought that I can handle the quadratic, so I don't really mind.
Yeah, no, fair enough. Can't have a calculator on the exam though, right? Remember, good old scientific calculators. I know, if only life would be easier, right?
Yeah, there's no way. What? No.
So, what you guys come up with?
I'm still working.
You're still
It's gonna
working?
Take a while.
Time is money, huh? So, how's this set up for this? Exact same, right? Generic dissociation of an acid. HA plus H2O, equilibrium goes to A minus and H3O plus, right? Our initial concentration is given, 0.01. It's all 1 to 1 to 1 to 1, right? So it's minus X. So at the end, we end up with X squared over 0.01 minus X, right? Equals our Ka. Everybody with me on this? In the theater of our mind, right, we end up with X, 0.01 minus X equals 1.8 times 10 to the minus 5, right? Good, then we have a choice to make. We have a choice to do the quadratic or a choice to do our approximation, right? So what's the difference in our Ka versus our initial concentration? It's about 10 to the 3, right? So we're right at the cusp there of can we do our shortcut? Now I saw some of you guys did both methods, right? You guys did the quadratic and you did the approximation. So what did you guys come out with when you did the quadratic?
Still working on it.
That's fine. So with the quadratic, what did we get? pH was equal to
3.38.
3.38, okay. And if we shortcut it, what do we get?
3.37.
3.37. So what's the argument here to make then?
It's nominal, even
Yeah.
at the cusp.
this is fine, right? But this is about the low limit of what we can do in terms of our shortcuts here, right? If you guys went to a difference about 10 to the 2, then we'd start to see bigger changes in our pH from the shortcut there, right? And we'd have to do the quadratic. Good? Okay. One more. A thinking one though, right?
So, quick question.
Yep.
So we're not necessarily looking just at Ka, like, oh, is it a small number? We have to also look at it, is it small in terms of the original?
Correct, yes. It's with respect to what your initial concentration is. That's what you have to compare there. Right? And if it's about 1,000 is the low limit of what you really want to abbreviate with, right? Or excuse me, shortcut with. Okay. So as a big shocker, one more here, right? pH of 0.1 molar. HCl, right? And there is the Ka for that. Okay. 30 seconds, ready, go.
Wouldn't it just be the same as the first question?
We got a different Ka, right?
Oh, different K, sorry, I read it.
Remember, it's the first thing you should always do whenever you approach a problem.
Think?
Think.
That does.
Assess.
That has not happened.
Uh-huh. Right?
I'm too brain dead for that.
Think and assess before you take too much time. Draw you guys' attention back. You guys done? The answer is 1.
Because complete dissociation.
Aha. So paying attention to what the question is asking. So take a look. This is hydrochloric acid, right? Which is one of our 6 strong acids. And so the assumption that we make is similar to the shortcut, right? We're making a similar assumption as with the shortcut method there. If we put HCl into water, it completely dissociates. Now, how do you guys know that this was a strong acid? Dr. H, I haven't memorized them yet. What's the Ka tell you?
It's really big.
It's 10 to the 6th, right? So millions, right, in the millions. So this is gonna be completely product favored. Do you guys catch what this means? That means for every 1, right, for every 1 HCl, right, we make exactly 1 H3O plus. You guys catch me on this one here, right? You guys following along? So do we have to set up an ice table for this?
No.
No. Can you set up an ice table? Sure, right? What are you gonna come up with? 1, right? Right? So paying attention to what the strong acid versus strong base versus weak acid versus weak base, what the K's tell you, all this kind of stuff is gonna be important, okay? Yeah.
I was going to ask, how do we know if it doesn't have like if it's not mixed with a weak base, wouldn't that change the pH? Because you had said like, it could be a little bit more acidic if it's.
Well, that's if you're doing a neutralization, right? Here we're just dissolving one thing into another, right? So we're just putting HCl into water.
Okay.
Yeah. Good, so then if you recognize that, all you do is take the negative log of 0.1 and that's equal to 1. Good? All right. So recognizing our 6 strong acids, very, very important. Recognizing what Ka tells us, also very important. So a little bit something different now, no more pHs for the moment. So write the balanced reaction for the neutralization. acid. And calcium hydroxide. And then identify your conjugate acid-base pairs. Stepping back for some math.
Oh, it's gonna have some.
You dumped that one there, Rachel, good job.
Thank you, sir, I'm at the top of my game today.
Yeah.
Considering where they were supposed to hold,
Isn't it like
what they were supposed to use.
SO? Okay.
Well, it's got acid, so it's HSO.
Oh, it's H and
So did I teach you guys the dumb way I remember how to name acids?
No.
No, I didn't teach you guys about the adic-itis.
The what?
Oh, man. So let's do a little bit, let's step back for a minute then.
H2SO4, guys.
So the adic-itis. So let's talk about this. So, what's the,
What?
don't worry, it makes sense. What's this, what's the name of that polyatomic ion?
Sulfate.
Sulfate. When I turn it into an acid, how many hydrogens do I have to add? 2, right? So if it ends with sulfate, it's sulfuric, right? So if it ends with ATE, the acid form ends with IC, right?
What about the ice?
What about the ice? There's nitrite. What's its acid form? HNO2. So nitrite becomes nitrous acid, right?
Is nitrous acid the same as laughing gas?
No, that's nitrous gas. Nitrous oxide is what that is, right? So, good, so there's your adic-itis, right? If you know your polyatomics, you can make, right, the acids forms, and then you guys know what the names are. What's nitrate? NO3, 1 minus. So nitrate becomes what? Nitric acid, right? This is one of our 6 strong ones. Good? Perchlorate becomes perchloric.
Yeah.
Mm-hmm.
Does anyone have the periodic table?
Have to remember the names. Have to remember where calcium is.
I'm just trying to remember calcium. Okay, calcium is so.
What was it?
Oh. Yeah, so there will be 2 OHs, so it'll be CaOH2.
Are you sure?
Does it have sulfur in it though?
Are you sure?
Does it what?
I'm just kidding.
I break that.
I'm just kidding.
I know I'm losing my mind, but I didn't think it was that bad.
Alright, so first things first, as you guys figuring out what the sulfuric acid is, right? And then figuring out calcium hydroxide, making sure that all the charge is balanced, right? So making sure we don't forget about our polyatomics. One of the most important things that you guys will see through all the rest of chemistry that you guys do, okay? Probably even some biology and all those other kind of chemistry-related classes that you guys will see, right? Phosphates and sulfates and all these things will show up over and over and over. Okay, so now comes the question of how to balance it, right? How much calcium hydroxide is going to react with how much of the sulfuric acid. Now, one thing to identify, right? Calcium hydroxide is we can consider it a strong base. So we have two OH minuses that come from the calcium hydroxide.
So we're gonna.
And so we need two H pluses, right? Now, does sulfuric acid provide us with two H pluses? Yes, right? It is a diprotic acid, okay? You see we have two of our H's here, right? What would be useful is for you guys to convince yourself of this. How are we going to know that both of those H's are acidic? We're going to need to draw our Lewis structure, right? That's the way that you look at this, right? H is bound to oxygens, right? Remember we talked about our oxo acids, right? One of the slides in the notes there, right? H is bound to oxygens tend to be pretty acidic, okay? Especially when you have a lot of oxygen around, like in our buddy sulfate there, okay? So if you draw the Lewis structure of your compounds, right, of what your proposed acid is, that's going to tell you definitively whether it's monoprotic or diprotic or triprotic, any of those kind of things. What's up?
So this might be a really dumb question. I might just be like thinking way too far ahead, going off on a completely wrong direction.
I don't know.
So we're dealing with a strong base and a strong acid, so we're assuming that salt is going to fall.
Yes.
I'm assuming that salt is going to be the sulfate and the calcium.
Okay.
How's it going to work since the sulfate is going to go back to a negative 2 charge in the calcium? Oh, I answered my question. I'm sorry, I'm an idiot. Never mind.
It's fine, you answer your own question. Okay, cool, so we'll pick this up on Friday there, we'll have a couple more problems to go through, and then you guys will be off on your way to wherever spring break is for you guys, right? Don't forget your quiz to do.